solar system. It's a great pleasure to welcome Christoph Burkhardt to give this lecture on solar system genealogy with isotope anomalies and meteorites. Christoph is based at the Max Planck Institute for Solar System Research. He got interested in meteorites after attending a lecture by Herbert Palme in Cologne. He obtained his doctorate in isotope cosmic chemistry at ETH Zurich, and he's had various positions in Chicago and Munster. He's won numerous awards, but the one that I saw that caught my attention was he got the Pallas Ryder Award in 2013 for the best student paper. So he's obviously spotted at an early stage in his career. So I'd like to thank Christoph and ask him to give his talk. Thank you very much.
Well, thanks, for the introduction. I hope everybody can hear me okay. It's a pleasure to give this Ed Scott lecture, and actually I interacted with Ed quite a bit at various conferences about this isotope business, and he was very interested always what came out of our lab also. So my background is in geology. And what do geologists do? Well, they take fossils and they try to reconstruct some paleo environments. And as cosmochemists, the fossils we use are meteorites, and the environment we want to reconstruct is the solar accretion disk and the processes that happen in them, in it to form dust into planets. And today, well, you can look at various ways on meteorites and get information out of it. But what we will do today is we will look at isotope variations in meteorites and really use these isotope variations as fingerprint or as a genetic tracer to investigate solar system evolution. And just to make the point that this is really something that is used all over, I looked into the previous Ed Scott lectures, and although they talked about very different things, all of the lectures so far that Ed Scott lectures had slides in them that talked about isotope anomalies. So really, isotope anomalies in meteorites, they seem to be key for investigating solar system evolution at really all scales. And today, I will give you some insights or some small points what we can use with these anomalies. And one would be we look at disk processes and how we can trace mixing. And the second would be we look at the genetic heritage of ungrouped iron meteorites. And if time permits, last, we will also use these anomalies to say something about what the heritage of Earth's volatile elements is. So why Earth became actually habitable, maybe. And to start with, we first need to define what we're looking at. So isotope variations come basically in two flavors. One is mass dependent, and as the name says, it's a function of the mass of the isotope. And the other is mass independent. And we use these two flavors of isotope variations to answer different questions. With mass dependent variations, we look at processes. And with mass independent variations, they are obviously not a function of the mass, but depend on other core properties like radioactive decay. And we use this to get ages. Or if it's nucleosynthetic anomalies, then we can use them as tracer. And this is what we will mostly do today. And just to give you an example of what the differences of these variations are, let's assume we have an element with 5 isotopes. Let's name it Ed Scottium. And you have the abundances relative to a standard. And now if something happens to the sample, some physicochemical process, we might fractionate the isotopes. And a mass-dependent isotope fractionation, here in this case, we will enrich the heavy isotopes relative to the standard and deplete the light isotopes relative to the standard. And this can happen more or less with every process where we can imagine. And now a mass-independent isotope variation or an isotope anomaly is an offset from expected mass-dependent behavior. So in this isotope here, we would have an isotope anomaly. This would be the expected value, but now this is more abundant than we would think just based on mass-dependent variation. And why this is so useful, I can show you in an example. So let's assume we form a planetary body. We accrete it from dust. And this body initially has this isotope composition and this specific anomaly. Now, the body heats up, and maybe some of the elements that we're looking at is lost. And that will, usually the light isotopes are lost easier because they react faster. So that what we will remain with is a body that is slightly heavier than what we started with. Now this body heats up, differentiates, and forms a core. And maybe part of this element that we look at partition into the core. So the light element partitions, light isotopes partition into the core, and the remaining mantle, the element in the mantle will become heavier again. Then we might have fractional crystallization and form a crust from which our sample then finally derives from. And again, we will have isotope fractionation. This time, the light isotopes will be enriched because the heavy ones will be taken down by crystals in the mantle. Then this rock makes it to us, and there's terrestrial alteration. And that might again lead to light isotopes preferentially over the heavy ones. That means a lot of stuff has happened to that sample, and all of these processes might fractionate the stable or the might induce mass-dependent isotope fractionation. However, what did not change over all of these processes is the mass-independent anomaly. So the isotope anomaly stayed the same. And this is the power of these isotope anomalies, because we can really use them. We can see through any planetary processes and directly link to the source reservoir, the source material, even though the rock has seen many, many different processes. Okay, now just a bit on notation. Well, in order to isolate an isotope anomaly from mass-dependent behavior, we need at least 3 isotopes, because if you have only 2 isotopes, this one and this one, then we cannot differentiate if this variation is mass dependent or mass independent. And because we are only interested in this isotope anomaly, we usually correct for any mass dependent fractionation. And we do this by an internal normalization. That means we just take another isotope and say, whatever this offset is from our standard, we reduce it to 0. And by doing this mass fractionation correction, we internally normalize everything so that only the isotope anomaly stands out. And this is what we're interested in. Now, historically, or the first element in the periodic table that has 3 stable isotopes is oxygen. And that's also one of the most important to look for these anomalies. Yeah, and this is probably something every one of you have done, or it's a staple in meteorite classification, oxygen isotope anomalies. And what is shown here is delta 17O. This is the deviation from a mass-dependent fractionation line, which would be here at 0. And then different types of meteorites now here are shown, all kinds of achondrites and iron meteorites. They have different anomalies, and this is very diagnostic. So this is used a lot in classifying meteorites, actually. And that is known since the 70s. So in this plot here, we have time in years and the number of isotopic systems or isotopic heterogeneous systems and the year of their discovery, and it's a cumulative plot. So oxygen was 73 with Bob Clayton, and that's for bulk meteorites. He showed in blue here that there are anomalies as well as in CAIs. And then if we concentrate on the blue line here, for a long time, nothing happened. And only mid-80s, the next element which shows an anomaly was discovered. And that is titanium. And for oxygen, we saw the variation is in the per mil range, the isotopic variation. For titanium, these are already measured in parts per 10,000. So the anomaly is smaller. And then again, for almost 20 years, nothing happened. But then around year 2000 and onwards, the field exploded. There were many more isotope systems where anomalies were measured. And this is because of a technical development, because then multi-collector ICP-MS was introduced, and that opened really the whole periodic table for isotopic investigations. And so this is kind of the golden age from 2002 to about 2016. A lot of elements were discovered to show these isotope anomalies at the bulk meteorite scale. And well, this is also when I did my PhD from 2008 to 2012. So I was in the midst of this. And now when we go to the last 10 years or so, there's still more anomalies discovered, more elements that show anomalies. But now we are usually going in the ppm world. So the isotope variations become smaller, but our machines become better and we can still resolve them. And also what happened in the last 10 years is that there's now more concentration of components of chondrites, like chondrules or matrix or amyloid olivine aggregates that also are investigated for isotope anomalies. Okay, but if we go back to these golden years, probably the most significant discovery that was made in the last 20 years, is this isotopic dichotomy between NC and CC bodies. So what you see here is a plot that you will show you will see several times in the next half hour or so. It shows anomalies in chromium 54 versus anomalies in 50 titanium. And each point in this plot is one distinct parent body. And what was shown is that in this isotope anomaly space, there's two fields. All the meteorites plot either in this blue field or in the red field. And what's even more important, both of these fields contain differentiated as well as undifferentiated meteorites. So that means early and late form bodies, iron meteorites, as well as chondrites. And this dichotomy is seen chromium titanium, but also just in molybdenum 95 versus molybdenum 94. And this has the advantage that we can also measure all the iron meteorites. So there are more points on here than on here. And this basically dichotomy, this isotopic dichotomy, allowed us to move from a more phenomenological classification of meteorites, where we have meteorites that have chondrules and meteorites that do not have chondrules, and meteorites that maybe have some relic chondrules. And in a way, I'm exaggerating here, but this is kind of when we classify people by looking at their haircut. So some have long hairs, some have short hairs, and some have maybe middle long hairs. And this does not tell us anything about the genetic relationships of these people. So this isotope anomalies really allowed us to look for genetic links between differentiated and undifferentiated meteorites. And well, Paul Warren was mastering this, and he came up then with this new classification scheme where he classified meteorites into carbonaceous and non-carbonaceous as like supergroups or superfamilies. And in both of these families, you have chondrites as well as achondrites. So that means you have long and short-haired people from the same family, but there are two big different families around. So what it means in the asteroid belt, from where our meteorites come from, we have two distinct families, NC and CC bodies, and they have a distinct isotope composition. That also means they cannot have formed at the same time at the same place. So the question is it a temporal variation? Did the NC bodies form first and then at the same place later maybe the CC bodies? Or is it a spatial variation where we form the two at the same time, but at a different place? And in order to differentiate these possibilities, we need to link our isotope anomalies with the accretion ages of these bodies. And this is shown here in this diagram. It's a busy plot, but I'll walk you through. So what we have on the y-axis is isotope anomaly here in chromium 54. And what we have on the x-axis is accretion time of these bodies. And again, each point in this plot here displays one distinct parent body. And the filled symbols are early formed bodies, and they are differentiated because they formed early. There was enough aluminum-26 around for them to differentiate, while the open symbols are the primitive achondrites, so not fully differentiated, and also the chondrites, which formed later. But what is obvious to see is first, there's again the two families. There's a red family and a blue family. And if you look at the timing, then these bodies formed in both families at the same time. So there's overlap in time of formation between both families. That means we have the case that they must have formed in coexisting but spatially separated reservoirs. And for an extended period of time. And it was already speculated by Warren that this might relate to formation locations inside and outside of Jupiter. We investigated it a bit further and maybe thought that maybe Jupiter's core formed within 1 million years after solar system start. And that would be actually consistent with observations that we have from disks, where we have probably planet forming gaps already very early on, and also could naturally explain the scattering of CC bodies then in the asteroid belt. But there are also other ideas more generally. If it's Jupiter or not, there must be some kind of pressure bump between these reservoirs that could also be caused by migrating ice or silicate sublimation lines. But for now, we can remain agnostic about what actually caused this separation. What we will investigate now first is how or what controls these anomalies in the first place. So why are different places in the disk different dust components around that form then isotopic bodies with different isotopic compositions? So that brings us to the first topic, really. How can we use these isotope anomalies to investigate disk processes? So the questions we need to ask is, what actually controls these planetary scale anomalies that we see on the bulk meteorite scale? And there are two end-member models around. One is, it is inherited from the molecular cloud that was heterogeneous. So the infalling material that falls on the disk, either at different times or at different places, had slightly different isotopic compositions. And that is somehow inherited in the disk, and then bodies at different places form in the disk with a different composition. And well, if we look at star-forming regions, then this is a picture of molecular cloud and star-forming regions in northern Cassiopeia. Then, and this is with Herschel, so what you see here is dust, basically. And then you see all these little dots where new stars are formed. It's a lot of filamentary structure. There's a lot of action happening. And we have then also regions with more or less no dust. This is a supernova bubble where it's expanding outwards and putting new synthesized elements again into the molecular cloud. So there's a lot of stuff happening, and it's not unimaginable that a collapsing cloud parcel that forms a new star has slightly different isotope composition. The other end member is that everything is happening in the disk and all the infall was homogeneous, but then different carriers were kind of separated in the disk because of gradients, like the temperature gradient, and only refractory grains might survive here, and all the more labile carriers might be evaporated. And that way we might have some basic unmixing and generate these variations. And that also brings us to the question, what is these variations actually controlled by presolar grains? Well, obviously, finally, it's presolar grains that carry these anomalies, but is it actual presolar grains that are heterogeneously distributed in the regions where these different bodies form? Or is it more disk products like CAIs or chondrules that are heterogeneously distributed and that these carry the anomalies that are dominating the bulk scale anomalies? So I looked into this problem a few years ago because now there's data for presolar grains and CIs or calcium aluminum rich inclusions, chondrules, these small spherules, and matrix that puts everything together. And then we can analyze how do these individual components relate to the anomalies of the bulk bodies. And the good thing is I spare you all the details and come just back to this figure of anomalies again. And what is observed is that the CC meteorites are offset from the NC meteorites in the direction of calcium aluminum rich inclusions, which would plot somewhere up here, and also in molybdenum somewhere up here. So, and this is a general feature that is seen in all isotope spaces. Yeah, these CC meteorites are offset from NC meteorites in the direction of CIs. This is not particularly surprising because everybody that ever looked at the carbonaceous chondrite knows there are CIs in, and if there has to be anomalous, then that will have an effect on the bulk isotope composition of the meteorite. And this is not something new. That was actually found by Niemeyer 1988. And he measured titanium anomalies in different types of carbonaceous chondrites. And he realized that there's a correlation with the aluminium content. And this trend is going, oh, this is me, passing through the CI value. So for titanium, obviously, that's nothing new. And CIs obviously influence the isotope composition of carbonaceous chondrites. But what was new now is that this trend is not only for refractory elements like titanium, but also for not so refractory elements that are not enriched in CIs like chromium. So this offset is not really limited to refractory elements. And this is an important observation. And we can, for example, chromium or nickel versus zirconium, molybdenum, or ruthenium, we always see this offset from the CC bodies from the NC towards composition of CIs. So, and it's not only CIs. Now, more and more data is coming in that also AOAs, which is another type of refractory inclusion, which is not as refractory as CIs, shares the same isotope composition of CIs. So what we can infer is that really the CC bodies are some kind of mixture between NC material and stuff up there. Well, there's two ways to interpret this observation, and they have been both put forward in the literature. And one way is, again, when we think about this homogeneous infall, then we will have thermal processing, where the idea is everything that falls in has a composition like the bulk solar system, and this is represented by Ci chondrites. And now this material, as we have it in Ci chondrites, is processed in the disk along gradients because there's temperature gradient, and then refractory carriers will be enriched in the inner solar system, while less refractory materials will be evaporated, and out of these evaporated isotopically anomalous materials, at one point CIs and AOAs will condense, and they then need to be somehow transported outside again to make it into the carbonaceous chondrites. So in that scenario where all this variation is because of thermal processing of CI like dust, the equation we can set up is the NC reservoir is Ci dust minus CIs. The problem with this is this scenario is full of unknowns because we don't know what actually the carriers are, how they react to different thermal processing, and how is it possible that refractory elements that we find in CIs are thermally labile and make it into the gas phase in the first place. So I think it's pretty difficult to make that work, and we need to know more about the carriers to evaluate it further. The alternative scenario, which I favor, is that we have these anomalies and we have a change in infalling composition. So the early infall, it's basically inherited from the molecular cloud, which is slightly distinct isotopically. And the early infall, which is represented by the isotopic composition of CIs and AOAs, is what's producing most of the sun and the disk. The early disk basically is spreading, and this early infalling material is therefore transported outwards. So this is one way also to bring CIs and AOAs out. But it's not only CIs and AOAs, it's basically the composition of this early infall is still solar chemically. That's why we call this IC for isotope, for inclusion-like chondritic reservoir. And then we have later infall, which would be NC-like. And as infall is always strongest close to the gravity, center of gravity, this will dominate the inner disk. So the CZ material in this scenario is a mixture between early infall, which is dominating the outer disk, and late infall, which is dominating the inner disk. This scenario also has its problems because, well, we can do the equation CC equals NC plus IC. So late plus early infalling stuff. The problem is, well, it's kind of an ad hoc assumption that the composition of the infall will change. But the benefit of it is it comes with quite a much lower number of free parameters than the previous model. And the prediction is that CC chondrites are mixtures, including CI chondrites. And whoever had a carbonaceous chondrites in hand knows, yes, they are mixtures. They are in chemical disequilibrium and there are different components in. And CIs are one of them. They're chemically and isotopically distinct. And we can then make a tie line and infer by lever rule how much NC and how much IC material is in the CC bodies. And we can not only do this for titanium and chromium, we can do this for all kinds of elements that show anomalies. And they all seem to indicate that this fraction of NC material in the CC reservoir is about 2/3 and 1/3 is IC material. Okay, and there's more evidence that CCs are mixtures at all scale because this data here in the blue diamonds is data for individual chondrules out of CV chondrites. And these individual chondrules basically show that this mixture between NC and IC materials is happening at the chondrule scale. Yeah, we have chondrules that have an isotope composition like NC materials, and we have individual chondrules that more or less look like CAIs. So this mixing is actually happening at the chondrule scale. And we can continue with that. This is again titanium chromium space. And these are all kinds of carbonaceous chondrite materials. And it could be, they can be understood as a mixture of chondrules, CIs, which would move up here, and CI-like dust. And there's a relation between the amount of chondrules and the amount of CIs that are in these bodies. So the more chondrules, the more CIs also. And this might be indicating of some kind of collection mechanism that for where these bodies formed by the streaming instability. So I would even go one step further, that not only RCC is a mixture between these components, even also the CI dust is a mixture in itself. And I think there's good evidence for that. So CI as a proxy for the Bark solar system, but is heavily altered. So all of the primary minerals, or many of them, are eaten away by aqueous alteration. But people found primary olivine in these CI chondrites. And when they measure the oxygen isotopic composition of these, they find that it has a bimodal distribution. So here is the oxygen isotope anomaly. And there are olivines in CI type chondrites as well as in Ryugu samples that have the same isotopic composition as CIs and AOAs. And there are olivines that have a more normal composition as other chondrite materials. And so I think we can see also that in CIs that there's a mixture between NC and IC materials. And if we understand or CIs as mixtures, then we might also explain the potential trichotomy that is seen when we look at iron and nickel isotope anomalies. So what is shown here is that CI chondrites and Ryugu samples seem to define a third field next to the NC and CC field. And it was either proposed that this means that they formed even further out in the disk, but alternatively, we think that if we understand them, these CIs as mixtures as well, then it might just mean that they got a bit more of some metal component of this IC metal. And we propose that this might indicate that they formed by photoevaporation instead of this accretion in the pressure bump where the other chondrites formed. So that might, the special composition of CI chondrites might be a signature of a special formation scenario for these bodies as the last bodies when the disk is disappearing. Okay, that concludes part one. So what controls planetary scale anomalies? It's infall and disk building and variable mixing of disk products. So controls, CIs, and the matrix. So I think we can conclude that CC materials are mixtures of NC and some IC material at all scales. And also, if this infall and disk building is producing these variations, then that also formed early, and that makes these anomalies or reinforces them as tracers for genetic relationships. And this is what we will do now in the second part. We will look at the genetic heritage of ungrouped iron meteorites. And yeah, so magmatic iron meteorites sampled the cores of differentiated bodies. And in this classic diagram from Scott and Wasson of germanium against nickel, we have different magmatic iron meteorites, and they define distinct fields. And we have about 10 main groups of iron meteorites. So all these iron meteorites sample just about 10 different bodies. And they are color-coded in blue and red. So blue again is the CC bodies and red is the NC bodies. But it's just 10 bodies. So there's a whole bunch of ungrouped iron meteorites, which might sample an up to 50 additional early form bodies where we don't have genetic information. So if we investigate that, we can ask questions like, is the dichotomy really universal? And we might be able to infer temporal or compositional variability between and within NC and CC reservoirs. And this is actually what one of our recently finished PhD students, Friedrich Spitzer, did. So we looked at all kinds of ungrouped iron meteorites, all the gray points here, and some of them volatile rich, so high germanium, some very volatile depleted, very poor in volatiles, and also very variable in nickel content. And if we take nickel content as a first proxy for core formation conditions, then more nickel means more oxidized core formation and less nickel, more reduced core formation conditions. And the approach was to measure molybdenum isotopes to see if they all adhere to the NC-CC dichotomy, and also get timing information about when the parent body is formed. And this is done from tungsten isotopes. And yeah, this is based on the decay of 182 hafnium, which decays to 182 tungsten with a half-life of 9 million years. And in a chondritic body, hafnium would just decay to tungsten, and it would slowly increase in 182 tungsten. Now, if the body differentiates, because hafnium is lithophile, it will not partition into the core, but all the tungsten, or tungsten is siderophile and will partition into the core. That means at the time of core formation, the core actually freezes the tungsten isotopic composition of the body at that time. So if we have a sample from the core that we measure now, that's the same composition as the body had when the core formed. So we can calculate the age when this body had this isotope composition, and we can infer as the timing of core formation. And from that, we can infer with a model again what the accretion time of the body might have been. The whole thing is a bit complicated. by the fact that these meteorites often travel long time in space, and therefore the isotopic composition is affected by irradiation effects. And we measured platinum isotopes as well to correct for these irradiation-induced isotope variations. And these are results, again, in molybdenum isotope space. We have NC materials and CC materials, and these are the grouped iron meteorites, or the main groups of iron meteorites, NC and CC. And now we have the ungrouped iron meteorites that we plot again here, and we see all of the bodies that we investigated adhere to this NC and CC fields. So the observation is all the ungrouped irons adhere to the dichotomy, and they also span a similar range in anomalies as the grouped meteorites. So there's no specific exciting observation that we find another reservoir or so. But what we have is now much more statistical power, because now we can, for the first time, basically give these orphans of the early solar system, where we don't know where they belong to, pinpoint them to families. So 16 of these ungrouped ions belong to the CC family, and 9 belong to the NC family. And yeah, the ages of these, we obtain core formation ages after timing of CI formation. And this is again the grouped meteorites. And now the ungrouped NC irons, and they span a similar age range, whereas these ages are not real core formation ages, these are later resetting. And then for the CC irons, again, these are the grouped irons. And these are the new data for the ungrouped irons, and they overlap and they indicate similar core formation ages. And there's a tendency that ages in the CC meteorites are slightly younger than the core formation ages in the NC meteorites, but it does not necessarily mean that these bodies formed later. It probably indicates that there's more water ice present in the bodies when they form in the outer solar system, and therefore it takes longer for them to differentiate, to melt and differentiate. And this more ice might be also apparent when we look at the core formation conditions, when we try to reconstruct the redox conditions under which these cores formed, then there's a lot of overlap. This is given in FO2 units relative to the iron wistite buffer. There's a lot of overlap between NC and CC bodies, but overall, the CC bodies tend to be somewhat more oxidized than the NC bodies, which might indicate that they accreted more water ice in their initial parent bodies. Okay, if we go back now to this molybdenum diagram, then we have, with the ungrouped iron meteorites, additional bodies that we can plot on here. And when we take all the different bodies that we know of, then we have 41 distinct NC bodies, and they follow this NC trend, or define a nice NC trend. And there's basically no scatter around this trend. When we now look to the CC line, this is a bit different. For there, we have 34 distinct bodies that plot on this line, grouped and ungrouped iron meteorites, achondrites, and also chondrites. But there, some of the error bars are obviously larger, but there seems to be excess scatter along around this line. And again, indicating the arrow to the composition of CIs, which is somewhere up here. There might be that obviously these carbonaceous materials are also mixtures again. And it might be that this scatter relates to mixing of different components. And in order to evaluate that better, we try to get rid of this S-process variation, which is along the line, and just look at the deviation from this. And this is done by the capital delta 95 parameter, which will be on the y-axis in the next diagram. And this is plotted now here. And when we do this, like it's the R process residual of these bodies. And then when we do this, we see that this variation in cap delta 95, so the deviation from the CC line in this plot, that this correlates with cap delta 17.0 again. And we can, on this correlation line, there's grouped iron meteorites, ungrouped iron meteorites, A chondrites, and CC chondrites. And again, we can explain this correlation by different amount of mixing of chondrules, CI-like matrix, and CEIs. So what we interpret this as is that achondrites, early formed bodies, like chondrites, late formed bodies, sample the same dust components in the disk. So it's not only the chondrites that may have formed from similar mixtures of dust components, but also the achondrites. Okay, to sum this up, part 2, we asked, is the dichotomy universal? And we proved this for about 25 additional bodies. The ungrouped iron meteorites, yes, they all plot either in the NC or CC trend. And is there temporal or compositional variability between or within the reservoirs? Then we have now more statistical power and think that really there's evidence that the CC reservoir seems to be more oxidized, so that fits to being formed further out where there's water ice. And chondrite and iron meteorite parent bodies seem to have formed from the same mix of dust components in the disk. Yeah, so we can explain everything with chondrules, CIs, AOAs, and matrix. And I think this is significant. Okay. Now the last part, quickly, heritage of Earth's volatiles. Can we say something about where the volatiles in Earth came from these isotope anomalies? Well, the first thing we need to address, how much CC material is in the Earth. And that's actually not so easy. That's something we tried a few years ago in multi-elemental isotope anomaly space. And we look, where is the green dot? That's the Earth, or the bulk silicate Earth, relative to NC materials in red or CC materials in blue. And when we do this for all kinds of elements, we can infer that most of the Earth comes from the NC reservoir, and only about a few percent, less than 15 or 20 for the Earth, come from the CC reservoir. But this inference is based on refractory elements. So this is about the bulk Earth, and this does not necessarily tell us something about the origin of the volatiles. These few percent CC material would be enough to explain all of volatiles by addition of outer solar system material, but we cannot really differentiate if all of the volatiles come from outer solar system material or addition of CC-like bodies to a really dry Earth that formed without, more or less, without volatiles or lost all of the volatiles it had initially, or if Earth actually accreted more or less wet, and what came from carbonaceous chondrites contributed some, but certainly not all of the volatiles. And yeah, that's a difficult and open question. And in order to differentiate these scenarios, we would need to know the fraction of volatiles from the CC reservoir. And this is only possible when we look at volatile elements. The issue is volatile elements like hydrogen, carbon, or nitrogen have only two isotopes. That means we cannot differentiate mass-dependent from mass-independent signatures, so not process from source signature. We can nevertheless try, and people did this, but then there's a second complication. There's no dichotomy, and we have ansotite, chondrite materials and carbonaceous materials that have the same isotopic composition and that both overlap with the inferred composition of Earth's primitive mantle. So what we need would be a volatile element with ideally 4 or more isotopes that we can make discrimination plots, and that this element shows an isotopic dichotomy between NC and CC materials, and then we can see where does Earth plot with respect to the NC and CC field, because if Earth plots in the CC field, that means all of Earth's volatiles come from the addition of CC materials to an initially dry proto-Earth. If Earth is in between, means there was some volatiles that come from the NC reservoir and some from the CC. And if Earth is only in this NC reservoir, that means there was basically a wet accretion from inner solar system material, and whatever came from outside did not bring many volatiles that it matters. So we thought about looking at zinc. Zinc is not really a water, but nevertheless, it's a moderately volatile element, and it is a plateau volatile element. What you can see here is condensation temperature against concentration for different meteorite types and the bulk silicate Earth. And you see that after at about 800 Kelvin, there's a plateau. And later on that plateau, there's somewhere water. So the idea is if we look at zinc, it's on the plateau volatile elements, we might even be able to say something about more volatile elements. Zinc, furthermore, is lithophile, and it's abundant in meteorites, so it's relatively easy to measure. And it's an iron peak element in terms of nuclear synthesis, and other iron peak elements like iron, nickel, chromium, titanium were shown to host isotope anomalies on the bulk scale, so we thought we'd give it a try. And it has 5 isotopes. And these are the results directly. So we struck really gold with this system. There's anomalies in 68 versus anomalies in 66. And we are not the only ones that are doing this. There were also other groups at the same time that are investigating this and found basically the same results. So there's a dichotomy in the moderately volatile element. There's NC bodies, differentiated and undifferentiated bodies with very different volatile content. But these anomalies define an NC field and a CC field. And now the question is, where is Earth? And Earth plots in between. And we can just, without looking at any concentration data, we can infer from this, this diagram how much of the zinc in Earth comes from CC and how much from NC. With this simple equation. And when we do that, we find, okay, zinc in Earth, 2/3 of it comes from the NC reservoir in a solar system, and about 1/3 comes from the CC reservoir. Now, we took this result and then applied it the same mass balance basically to hydrogen and nitrogen. Although it's not straightforward to use these because there are only 2 isotopes and so on, and it's the general systems. But nevertheless, if we take the information we get from zinc and do the same balances for these elements, then we also find that bulk silicate Earth fraction of CC derived material for these elements is again about 1/3. Error bars is large, and this could be a coincidence, but nevertheless, if it's true and zinc already is on the volatile peak can be taken as a proxy also for more volatile elements, then this would indicate that generally the volatiles in Earth is about 2/3 from the NC reservoir and about 1/3 CZ reservoir. Now, how much CZ material does this correspond to? Well, this depends on how wet the CZ material is that we accrete, and therefore we need now concentrations. And depending on the concentration of zinc in different CZ bodies, we get different amounts of bulk material that bring these volatiles. So for CV chondrites, we get about 12%. For CI chondrites, it's more volatile rich. We get about 5% that's needed. And this independently is in agreement with the information we got from the refractory elements. So there seems to be a few percent of CZ material in the Earth, and this brought about 30% of Earth volatiles. Okay, when we combine this, now the zinc as a volatile and the chromium as a or titanium as non-volatile elements, then we can make the Earth out of a mixture of ansatite chondrite-like material isotopically and 5% CI-like material. Okay, to finish off, we identified or we made use of these isotopic anomalies in the volatile element to figure out how much of Earth's volatiles comes from the NC and CC reservoir. And our result is that there must be endemic volatiles present in the inner solar system in the NC reservoir in the building blocks of the terrestrial planets. Okay, now my time is certainly up. These are the big take-home messages. I hope I convinced you in this little tour de force that isotopic anomalies in meteorites record essential information about disk building, transport, and mixing of materials in disks and in fall. And I hope I convinced you that you can understand the CC reservoir as a mixture of NC and IC material at all scales. And we used these isotopic anomalies to infer genetic relationships of ungrouped iron meteorites. And we have now a total of over 40 different NC bodies and 34 CC bodies. And that number is growing as people do more measurements on more samples. And when we looked a bit more into the details of these anomalies in these bodies, we found that early and late form bodies, or differentiated and undifferentiated bodies in these different reservoirs, seem to have formed from the same mix of dust or nebular materials. So in early and late formed materials, there must have been some kind of similar mixtures of dust. And lastly, we took isotope anomalies as a proxy or to infer something about the heritage of Earth's volatiles, and found that about 2/3 of volatiles in Earth are from the NC reservoir and about 1/3 from the CZ reservoir. With this, I thank all the meteorite enthusiasts out there that make this field so exciting. Fund museums for donating samples that we dissolve in acid, funding agencies, and the MPS Planetary Materials Group for making it all happen. And there's 2 papers that will be shortly out, and from which I took a lot of the stuff that you saw here. And lastly, if you think there's a lot more to do in this field, and if you think this might be something that you would like to do, feel free to contact us. And with that, thanks for the attention, and I'm happy to take some questions.
Christoph, thank you very much for a marvellous, really inspiring talk. Just like to tell everyone that the chat box is now open, so if you want to put your question in there for Christoph, that would be great. I had a quick question myself, and that is that I noticed you didn't spend a lot of time talking about Jupiter. So do you think the role of Jupiter is less important than was originally thought in keeping the NC in the...
No. Yeah, I intentionally did not speak about Jupiter because that story is told already several times. I think Jupiter is super important in shaping our solar system. I mean, Jupiter is the king of planets. It's the biggest planets that we have, biggest planet that we have. And it must have formed early, and it's there. So it certainly influenced the shape of our solar system as we have it now in various very important ways. So I think understanding Jupiter is key for understanding the structure of the solar system and setup.
Okay, fantastic. So just remind people the chat box is now open. So if you want to ask a question, please do that. Everyone's very quiet. You start to stun them with all that amazing data.
Yeah, that was a lot of isotopes. I apologize for this.
So Paul Warren has asked, great talk, he said. How far along have you taken the zinc isotope work with respect to Mars?
Yeah, I think we published paper 23 that deals explicitly with Mars. I left it out here. The point is for Mars, it's more volatile rich than Earth. There's more zinc, and it's further out than Earth, so closer to the asteroid belt, or you would think to the CC reservoir. But actually, zinc in Mars is basically exclusively NC. So Mars does not seem to have acquired a lot of CC materials. So there's a disproportionate accretion of CC materials to Earth and Mars. What this really means is something for the modelers, I guess. But it means that maybe Earth accreted a few larger CC bodies relatively wet, and Mars did not, basically. And now I just submitted an abstract to Goldschmidt where we look also at HED meteorites, and there it's the same. There's also a paper published by the French group already. It looks like Vesta also is basically dominated by NC volatiles.
Alan Rubin has asked, an interesting consequence is that both differentiated and undifferentiated bodies accreted in the inner and outer solar system. One would have thought the accretion rates would have been different. If you've got a comment on that from Alan.
Yeah, I mean, it could be that the accretion rates are different, right? Or did I not get there?
I think he's saying that based on your data, the accretion rates look very similar, I think. Yeah, and he's puzzled by that, I guess. They want to be different. Ming Ming Zhang has asked, what is the IC component? IC equals refractory inclusions?
No. Yeah, that we named this inclusion like chondritic. So the isotopic composition of that component is like the one of CAIs and AOAs. But overall, the chemical composition is solar. So that would be the early infalling material in our theory. And CAIs and AOAs are just the refractory part of this component or this reservoir. And there's also material that is less refractory, but also has this isotopic composition. At least I'm convinced that this exists, because if the CISNAO is condensed out of some solar gas, then the stuff that condensed at a later time or at lower temperatures also must be somewhere, and that material has the same isotopic composition. And I think looking for this in metals or for the metal component of this reservoir will be something for the future that people should look into.
Telson has asked, any process after infall that may produce new mass-independent fractionation signatures in solids?
Yeah, well, we have galactic cosmic rays or exposure to them. They obviously can also induce some mass-independent variations, but they will look different than the ones we see from the nucleosynthetic variations. And we can correct for them. I mean, for the meteorites, they obviously some of them are exposed for a very long time, and therefore we modify the isotope composition. But this pattern that we get from the cosmic ray exposure is different than the nucleosynthetic signatures, so we can resolve the two.
So Robbie Hanna is not so much a question as a compliment. A wonderful talk. I personally learned a lot that will be very useful for my work. So thank you. Looking forward to that FSR paper. So, yeah, there's a question about how you can get some new meteorites there. Orkan Umaran, I hope I got that right. Outstanding talk, especially for us fluid dynamicists trying to link processes to the evidence. I have no question, but I still do not understand enough. But that helps me to orientate myself, and you can see enjoyed it a lot. Patrick Mann, great talk, thank you. My question is, how do you form infalling material that is only isotopically distinct but chemically similar? Isotopic anomalies will be hosted in pre-solar carrier phases with certain chemical compositions.
Yeah, but yeah, it's like for the chemical composition, everything, if we look at the cloud, is more or less than about solar. But for these isotopic variations that we look at the bulk meteorite scale, they are on the level of parts per million to parts per 10,000. So this is very small differences. Overall, like 60 years ago, everybody would have thought it's all the same isotopically and chemically. Now we see there's very tiny differences in the isotopic composition. That does not mean that it also comes with chemical differences, because overall, no matter where the stuff is coming from, we are, yeah, I think the chemical composition of the infalling material will not be noticeably different.
Okay, well, it's sort of kind of related. Romy Hanna has come back with, do you expect a gradation in IC isotopic signature among the CCs related to their accretion distance? That's just the CC reservoir, or is it pretty well mixed past Jupiter?
Yeah, I think you need to repeat the question for me.
Okay. Do you expect a gradation in IC isotopic signature among the CCs related to their accretion distance? Or is it pretty much well mixed past Jupiter? So I suppose that just relates to the CC.
Yeah. Well, I mean, there's gradation in terms of, because different types of carbonaceous materials got on top of, well, different amounts of CAIs. So some have more and some have less CAIs. And for some elements, that certainly matters. The question, how it really, what's the composition out there, is one that I would like to answer. And for that, a comet return sample would be the best thing to have in the lab. I don't know when it happens, but obviously, yeah, I don't know how well mixed the outer disk is. in the scenario that we propose, if the early infall is like sun-like or CI-like, and this is through viscous spreading going and dominating the outer disk, then I would imagine that the outer disk is somehow similar to CAIs. But I don't know. It could also be that maybe there's some late infall that just happens on the outer disk again with different material, or I don't know. But a comet sample would be great to test this.
Definitely would, yeah. Patrick Lebrun has asked, do you think the reservoir's isotopic anomalies are at all inherited from different pre-solar precursors in falling at different times, i.e. R process or S process, etc.?
I think you have to read that again to me.
Yeah,
it's
sorry.
late for me already.
Yeah, no, I know. It's been a year talk, yeah. Do you think the reservoir's isotopic anomalies are at all inherited from different pre-solar precursors in falling at different times? I guess the pre-solar. Yeah.
I mean, we have isotope variation. That means if we think it's inherited from infall, that also means it's probably in slightly different carriers, or there's, in our scenario, the early infall, the IC-like infall would be more enriched in supernova-produced nuclides than the late infall, which would be more enriched in S-process nuclides. But again, it's very tiny differences. Yeah, you don't need much to produce these variations that we see. Yeah.
So Orkan Umaran has said, aerodynamic drag also brings in materials from the outer disk, especially around the settling midplane. This problem is still being examined, or just on that, sorry. This problem is still being examined in the disk structure turbulence community, more to learn. So more a comment there, I think. Sasha Croaks is asking, great talk. Do you expect the matrices in NCs and CCs are isotopically different or CI-like? Do you want me to repeat that?
Yeah, that's another good question. And I think work on matrices in different types of chondrites to isolate it and measure the isotope composition is the way to test this, really. It's a difficult one. And well, there's not much. Well, a good way would be to look at NC chondrites with a lot of matrix. There's not many, but there are a few, and to test that. So I don't know, but there are people that say all the chondrites have like a CI-like matrix, and I might tend to agree, but it needs to be tested.
Yungbin Gao has got a question about the cosmic ray production correction. He says correction for cosmic ray production could be large for some of the isotopic anomalies, especially iron meteorites with their long exposure ages. How does the correction affect the precision accuracy for those very small anomalies?
Yeah, well, it depends on the element. For some elements, it doesn't really matter. For some, it's more severe, like for tungsten, obviously, for the dating, it's more severe. But the data I showed was already corrected, and all the error bars I showed included this correction. So the effect is severe, and if you underestimate or overestimate, you might be off. But I think with the platinum, we have a really good way for iron meteorites, at least, to correct for exposure. And like for molybdenum, it's on the order of 10, 20 ppm or so, these corrections. It is relevant, but we can deal with it.
Okay. So I think that's the last question there in the chat box, as far as I can see. You generated an awful lot of questions. You generated a lot of people who turned up and a lot of questions. So I'd like to thank you again for an absolutely fantastic talk, very thought-provoking and lots of amazing data. And like Hannah said, I'll be taking it away myself and having a good think about things. Thank you.
Yeah, and I think it was a lot, and it's good that it's recorded, so maybe people can have a look again and think more. And yeah, feel free to contact me out there if you have more questions. And yeah, I can advertise this Space Science Review paper about infall and disk processes that should be coming out soon, where a lot of what I present is maybe even in a better understandable way presented.
I think that's going to be a very heavily cited paper, Christoph. Thank you very much.
We'll see.
Thank you.
Okay. Thanks a lot.